Hello, this is a video on Chapter 2, Section 1, where we will be talking about the tangent and velocity of a graph. Before we start off, let's first define what velocity is. Velocity is the speed of something at a given direction. In other words, it is also the rate of change of an object at a given time. In order to find the velocity of an object, we use two methods through the secant lines and tangent lines of a graph. The secant line is the line where it crosses the graph at exactly 2 points. This helps us find the average velocity of the object. So, if we were to say this is a function of an object and y is defined for height and x is the time, we have the coordinates of 4, 2, and 2, 0. That means at 2 seconds, the height of the object is at 0 feet. Let's say this is feet. And at 4 seconds, the height of the object is at 2 feet. And through the line that crosses between these 2 points, we are trying to find the slope of the secant line, which also tells us the average velocity for it. So, how do we find the slope? Easy. We use the slope formula, which is defined by y2 minus y1 over x2 minus x1. If we were to plug these coordinates in to this equation, we'd get something like 4 minus 2 over 2 minus 0, which gives us the average velocity of 1 feet per second. On the other hand, the tangent line of a graph helps us find the instantaneous velocity of the function. And since it only crosses at 1 point, not at 2 points, it gives us the exact velocity of the object at that point. So, here we have almost the same type of function with the coordinate of 4, 2. And if we were to just estimate the slope of this tangent line, which is around, let's say, 3 over 2, that would be considered the instantaneous velocity for this function. So next, we'll be going over a couple of examples and be using these two concepts to find the velocities of certain equations. Okay, so for our first example, we have if a ball is thrown up from a building 25 meters tall with the velocity of 16 meters per second, its height in meters t seconds later is given by the function negative 16x squared plus 16x plus 25. Estimate the instantaneous velocity at t equals 1. So, since we can't use any limit functions yet or things like that where we can go directly to find the instantaneous velocity, we use the slope of secant lines to estimate the slope of the instantaneous velocity through finding the pattern and seeing the trend. So, we must find some t values that are close to t equals 1, and then use these values to calculate the slope in respect to t equals 1. So, let's first plug in 1 to the equation. That will give us the coordinate of 1, 25. And then we use several different points that are close to t equals 1, such as 1.5, 1.1, 1.01, and 0.5, 0.9, 0.99, which comes from the left side and comes from the right side. We plug these values in to the equation, and let's say for 1.5 we have the value of y as 13, and in respect to this coordinate we find the average velocity, which gives us negative 24. On the other hand, we have 0.5, which gives us a y value of 29, and that will give us the average velocity of negative 8 meters. Since the distance between these 2 points are quite far, the instantaneous velocity is not really considered accurate. So we have to go farther, make the distance smaller between these 2 points to give a better estimation of the instantaneous velocity. So let's go a little smaller here. So we have 1.1 and 0.9. When we plug these two values in and get the y value, we then calculate the slope to having negative 17.6 meters per second for 1.1 and negative 14 meters per second for 0.9. We must remember that all of these velocities are in respect to t equals 1 because we are trying to find the instantaneous velocity for it. So, lastly, we go even farther, which is 1.01 and 0.99. Once we plug in 1.01, we get the slope of negative 16.16, and when we plug in 0.99, we get the slope of negative 15.84. And look, we have an interesting pattern here in which these values, the slope values, are slowly approaching negative 16 meters per second. So we can estimate that the instantaneous velocity for this function at t equals 1 is negative 16 meters per second. Okay, so for our next example, we have a different variation. Instead of it telling us the function, it gives us simply a table of values. So for this example, it says, the table shows the position of a runner at t seconds. Well, assuming that, let's ignore the realisticness of this table, how do we find the instantaneous velocity at t equals 3 without a function? Well, since it gave us a table, we start from here. Since we're looking at t equals 3 seconds, we're going to be focusing on the intervals or the average velocities for it. So I would be choosing the average velocity of t equals 2 to 3 and 3 to 4. We want the medium number or the middle number to be 3. So then after we calculate the average velocity for these two intervals, we can then calculate the average for these average velocities to estimate the instantaneous velocity at t equals 3. Some of you might ask, why don't we do 1 to 3? Instead, we're doing the interval 2 to 3. Well, if you think about it, 1 to 3 is less accurate than 2 to 3. Since secant lines, we need the distance for secant lines to be as close as possible, which in this case, it gives us the closest distance of 1 second. So we want to be as close as possible to reach the tangent value. So let's go on and try to find the average velocities for these two intervals. So for 2 to 3, we have 8 minus 5 over 3 minus 2, which gives us the average velocity of 3 meters per second. While for this interval, we are calculating 15 minus 8 over 4 minus 3, which gives us the average velocity of 3 meters per second. After we found that, we then find the mean between these two values, which I hope you guys know the equation for this is to add these two together and divide it by 2, which gives us perfectly the instantaneous velocity of 5 meters per second. Thank you for watching this video. I hope you can do my worksheet pretty smoothly